All right, welcome back. Some people have asked me to look at some of the sample homeworks and perhaps even go through the process of showing them to others. So who in this classroom doesn't mind my showing? Brian, shall we look at your attempt first or attempt two?
Attempt two is just a picture.
Shall we look at your picture? Yes? Okay. It's a picture of you at the beach. Why do we need to see this? Really? Here is a picture of you at the beach with Chinese characters. Is this politically incorrect? I'm sorry, but I don't think downloading is working here. Or perhaps it is working, but oh. Yes, why is it Chinese?
I was testing it out to see if it would give my Chinese character strings.
Oh, it looks like it's working.
Yeah.
That's great. So now we can see your Chinese characters, and now let's go back and see your actual code. Is that in here in attempt 1? Alright, so let's have a looky-loo at that. Now, to see the code, what do I have to do here? Download? Or maybe it's on the right.
I pasted it and I uploaded it.
Well, let's not download it just yet. Let's just look at it. So we have, what am I looking at here? This is you built a Swing application. That's above and beyond, but it's very nice. Where is the actual business logic of this program? Oh, here it is. Here it is. Here it is. So there's where you do the exclusive OR, and then you create a char, which goes into the char array, and so you take this entire PT and you convert it to a char array where PT is some string. Why did you use the term PT, I wonder?
Oh boy, what did I send you?
What were you thinking? And where's the decode? Or you use the same thing to decode as you do to encode?
Yeah, I use the same thing, decoding.
Ah, encryption algorithm. Here it is. Did other people write Swing applications? Oh, good. What?
Rich did.
Rich? Oh, well, let's look at Rich's then. Well, how come we can see yours? We couldn't see Brian's. Oh. I mean, this just comes through very nicely, but it's also Swing.
So if you go to the very bottom, it's the actual algorithm.
Well, if it doesn't swing, it doesn't mean a thing. The byte decode, encode ENC key, get text, decode text, ET get text, PT set text. Why are people using PT? Oh, that's plain text, of course. Of course, PT, plain text. Yes. Ah, here it is. Here's your exclusive OR with the key. So it's working. And did you also provide us with some sort of image? I have to run it in order to see if it works. That means I have to like copy and paste it and then compile it. Okay. That's a lot of work for a grader. Don't you think you should show us sample output? How about like a Word document with like the, that might work, right? So we'll do this new Java class, and we'll call it something meaningful like foo, and then we'll paste in your thingy, and then it says it doesn't like that because it doesn't match the name, which of course it doesn't, because you called it something not foo, but we'll change the name to foo because that's a good name. And then we'll hit run, and this will work, right? And if it doesn't, it's minus 10, because you made me compile it. I've devised a whole new grading system. I take off 10 points per day late, and so eventually after 10 days you have 0. After 11 days it's minus 10, and then minus 20. So we need new letters. I think some students will be getting an M. So let's see. In code.
Are we gonna have projects or tests?
It's all projects. How do I make this work?
Type something in the first black box.
Here?
Yep.
This is a test. Oh, how cool. Encode. Decode. This is a test. Encode. Decode. Decode. Encode. Decode.
And then you can change the key at the top.
And now we can change the key. And maybe 1111. Encode. Oh, key not in correct format. Blah, blah, blah. What is the correct format for a key?
So I left it all hex, so you put like a decimal if you want, or you could put like 0x13 or anything like that.
13?
So,
Encode.
but just 0x13, get rid of the rest of the stuff.
0x13.
2-bit hexadecimal.
Yeah.
Encode.
2-bit hexadecimal.
What?
The restriction is 2-bit hexadecimal.
0, 1, 1, like this?
2-bit.
2-bit. 0, 0, 1, 1. Is that okay? Alright, so how many ones can I put in? No, not that many. So how many ones am I allowed?
So I sent it as a byte, so that's 0.
Oh, it has to be a byte.
Yeah.
So a byte, that's like 8 bits, right?
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, like that?
That
No.
should.
How many bits in a byte again?
You can do decimal too.
Apparently not. Decimal. Okay, how about this? 12. Can it do that?
We have to type something first.
Okay.
There you go.
Yay. Well, that's very nice. Thank you. That's a good one. Should we keep looking at this? Yeah, I'm hoping there's going to be one I don't actually have to compile to test. Kyle, did I look at yours yet? Oh no, I have to compile it? Hey guys, listen, maybe it'd be good if you gave us like a sample input and output so that I wouldn't have to sit there and compile everything. Because you can see how tedious it is, right?
Can we just lie then?
Well, no, because you're going to take a snapshot of the screen while it's executing,
Oh.
right?
Oh,
No?
I didn't know what
If you got this thing running, right, it'd be really cool if I didn't have to like sit there, download it, and compile it. So if you're
So you don't want us to upload Java files?
you can upload the Java files, but it would be better if you could give me a picture of what it looks like in and out.
Is there an easy way to make like a runnable jar or something?
You could if you want me to download and run your jar files.
Yeah.
But why not just, take a picture of the screen and upload it?
Because what if we have like a longer thing?
You could use Jing, right? And then send me the link. And then I could just run the video if that's easier. Right?
Or you want the code also, right?
But if you've got the code and a link to the Jing, then I could see it and I'd know it works. And I wouldn't have to download it to run it, and I could look at the code. Alright, so now what do I have to do to get this? Download, and then what? Open. Always open files of this type. Open. Geez, it opens it in Word. That's bizarre. Okay. This is more along the lines of what I was expecting. I wasn't expecting to see a swing application. But that's good. I mean, I like the swing. It's just this is a little easier to deal with. So is this about what I'm going to see when I look at other people's code? Should we keep going? We're there, right?
How many other people are there?
Well, there's a bunch. There's the distance learning people.
They don't count.
What do you mean they don't count? Distance learning people count. But it doesn't. Apparently, they're not submitting their code.
I submitted a second one with a picture. Photo.
There's one with a picture.
I just hit something.
I don't see it here.
Well, I just
Is that here?
tab 2, I guess? Yeah, that's fine. There's a link. Like the
Oh, okay. A link. That's good. So we click it. What does that do for me? Oh, that looks right. That's very nice. Okay. Back to work for us. So for next week, I'm considering this idea that you guys would have a homework assignment, and that the homework assignment would be a solution to the maze, maybe better than the one I have, using the shortest path, as you had suggested. Your suggestion, right? Right?
shortest path.
Shortest path for the maze.
Didn't you say that was like really hard?
No, it's not really hard. It's NP complete, and it's as hard as an exponential search. But since we're starting with only a 20 by 20 matrix, it's not computationally intractable for a fast machine. You might have to let it run for a few seconds, but that's it. Yeah. So we'll call it homework 3. Homework 3. Homework 3. There we are. Modify the maze, or write your own maze solver if you like. Modify the maze solver to provide a shortest path. And you know the Micromouse people are doing that, and they're doing it with a real robot. They don't even get the benefit of having the whole maze given to them geometrically in advance. To find the shortest path between the start and end positions in the maze created by Maze Generator. And Maze Generator is the program that we were just looking at under arrays. Yeah, here's Maze Generator. Got that? Everybody understand the problem? Now you don't have to output images. The output, well, I guess you might say it's an image. The output can be ASCII text. It can be text, just like the output that I've got in there right now. The way I convert image data over into, well, text data over into images is given by a program that I wrote today. So that's called maze to image. And what I can do, just to make sure you have a copy, is paste maze to image. If you want to convert a maze to an image, you can use POW, maze to image. But you don't have to. I just put it in there for completeness. And use it or lose it. I don't think it's.
So it's the maze generator one.
Yeah, maze generator you already have.
You just have to change the search to make.
Yeah, let's make the search better.
So are we doing the straight line?
Well, I showed you how to do the straight line because I wanted to make sure you knew what a parametric expression for form for a geometry should be. The question of whether that straight line is of any use to you or whether you want to use it is another matter.
So what would a good way, a possible way?
What's a better way to generate? Well, we know the straight line gives us the shortest path between 2 points, but unfortunately the straight line that we generated was considered a diagonal line, not necessarily the kind of line that we can go in because we're constrained to go through the maze and using the Manhattan distance. So let's see if we got. Let me see if I got this postulated properly here. When is this thing due? The 6th, right? And at 5 p.m. Is that good? And there you go. Submit. And we are there. A nice little homework assignment. And there's the buffered image, which shows you how to go and well, this says get the maze image. So once you have your characters, you can display it as an image and you can make it look nice. But you don't have to. I just think it's nice to have a real image from these symbolic representations of the maze. I even wrote comments. Look, isn't that nice? Ooh, good for me. So there it is. Now, Kyle, you asked the basic question, how shall we create all possible paths for the maze? I would think that the thing to do would be to save the shortest path that you've encountered so far. So first generate a path, and then figure out how many increments there are, its total distance, total number of moves, and then save that path, and then proceed to search for the next possible path with small perturbations, and if that's shorter, then use that path.
So where you do something sort of like a max min,
Yeah, you could. Well, when you look at how the maze solver works under maze util, I think there's something in here. You invoke it. It's called solve. There it is. So the way I solve the maze, I start with the start in here, and I put it into the maze traverse. So to call get start, what I do is I traverse the entire maze and search for an S. When I find the S, assuming there's only one start in the whole maze, and there is, and only one end in the maze, and there is, then what I do is I use that point. Remember that Java AWT point is an integer point which has an X component and a Y component. So it's point.x, point.y. This is how we generated all the points when we used the parametric expression. And so maze traverse does all the work. And then the direction, it's left, right, up, or down. Those are the directions. And here we check if something is a valid move, and the question then becomes, how do I know if it's a valid move? Whoa. What just happened? I pasted and I shouldn't have. How do I go back to where I was? This is terrible. Look what he did. Here. How do I know if something is a valid move? Control B takes me to the definition. So what do we do to do the check? First we check the range on the row. It has to be less than the width or greater than 0. The column has to be greater than 0 and less than the height. There can't be a wall. So it's a valid move if you don't leave the what we'll call if you don't create an array out of bounds exception. It's valid as long as you're not trying to move through a wall. So that's how you check if you have a valid move. So if you're at any location, X and Y, you can check to the left, you can check to the right, you can check up, and you can check down. That's how you generate a valid move. And so then the move says, look, if it's a move down, I can increment on X. If it's a move right, I can increment on Y. If it's a move up, I can decrement on X. I'm assuming X and Y 0, 0 are in the upper left corner. That's why moving up is actually, you know what? I'm thinking this is backwards again. I should probably get my up and down correct. But it's alright. As long as you've got all the different possible directions, it shouldn't matter. So this is going to check in advance of the move, and then it's going to do a maze traverse. Now maze traverse says, this is recursive, right? He goes back and proceeds to say, if I found that I am done, then I can just return and print I am done. And we know when we're done, when the point that we arrived at has the end point on it. That's the done signal. So I can compute start and I can compute doneness pretty easily by checking for the end point or the start point. You can see how I check for the start point. I just check every single cell, and if it's a start point, then I get R and C and I paste it back in and return it. Let's see now. What else do we got? Maze util. Up, down, left, right. So what this doesn't do is it's not storing paths. It's just finding a path. And it gives you a path, and it's not a particularly good path. So if you want a shortest path, you could store all possible paths or store maybe the shortest path you've encountered so far as you proceed to look at all possible paths. What do you think of that?
It's fun.
I think it's fun. Very fun.
Would it be good to use a stack?
You could certainly use a stack. That is absolutely a good way to do it. You know, if you wanted to, you could generate all possible paths by exploration and store them in a vector, and then sort the vector by the path length, and then proceed to just take the shortest path. But the way I do it is if you're generating all possible paths and you encounter a path that's shorter than some prior path, that's the path you store. And then you can keep looking until you find something shorter. So there's a couple ways to do that. I think it's a fun little project, and I think you should have, get creative with it. One way I do these sorts of things is I use an A-star search, which is a heuristic search, but you certainly don't have to do that, and that's a fancy computer science-y kind of thing. That's what I did in the book. If you look up in the book under the index, you look up under Martelli algorithm, and that is an A-star search. So so let's see, where did we get to last time? There we go. If you go into IP.main, what you'll do is you'll get into a image processing program that I wrote some time ago, and this is one about which the book is written. When you run it, you get this interesting looking interface, and if you expand it just a little bit, you see the cameraman. If you type G, that allows you to open up a GIF image, and then if you search for the GIF image of your choice, here's one called Lighthouse. You can see a little lighthouse. Sort of a lighthouse. Nice, right? So now you ask the question, how do you build an interface to something like this so that you can start to do image processing? This is a sort of a basic sort of question. A couple ways you can do it. One thing I like to do is I like to create keyboard shortcuts for doing the image processing. So if I type escape N, that does a negation. Escape N negates again. So that's a basic image processing operation. There's a bunch of them in here, and they're organized by menu item. And one thing you might notice when I click on a menu that has an arrow next to it, more menus pop up. And that's called a hierarchic menu item. And with hierarchic menus, you can organize your image processing operations, and they can be a little bit awkward, but you can essentially go and find operations that are all related to one another because it's organized. So the hierarchic menu item allows you to organize the operations, and these escape keys, like escape 9, will do a 15 by 15 Gaussian convolution on the image, which is really a fancy way to say a low-pass filter. So let's see if that works. And it does. And the low-pass filter makes it look kind of blurry. And if I type R, it goes back to the original image. And if I type G, I can always restore back to something or get something.
How's that the original?
Well,
Or opening new thing?
yeah, it was. I went back to the cameraman image.
Oh.
Yeah. So I've got interesting and wonderful effects. Here's one called a height field. And the height field essentially maps the different grayscale values to different heights. And this is represented with a boundary representation known as polygons. Let's see if we can do this. Oh, there they go. And it's very fast. I think I can click on it. There we go. So now you can see the wireframe representation. And then I can do smooth shading. And this is texture mapping. So now the height fields of the polygons are actually colored so that they're consistent with the image that we're looking at. You can kind of see the space shuttles in there. And we got FFTs, and we got wavelet transforms, and we got rotation and affine transforms. and more convolutions and low-pass filters and high-pass filters and edge detectors. Here's one called a Roberts edge detector. And this is a histogram equalization. And then if you want, you can do a threshold. Let's see if I can do a threshold. Maybe I can't do a threshold because I don't remember how. Threshold should be like under color. RGB, gray, negate. I'm thinking it's escape T, but I don't see it here, so let's just try it. Escape T? No? I was thinking there's a threshold in here. I just don't remember where I put it. Threshold says if it's below a certain amount, make it 0. If it's above a certain amount, make it like 255. You found it?
Yeah.
Oh, there it is. Threshold. It's escape T9. Oh no, escape T should have been a threshold. Escape T9. Oh, there it is. So now with a threshold like this, if I had a start point and an end point, I should be able to find my way through the pixels in order to be able to solve the maze. Right? Maze algorithm. Only it's the inverse maze algorithm, because what it's doing is it's starting with an image, right? Instead of starting with the maze and generating an image, we're starting with an image and solving the maze. Cool, right? And it should be possible to use a paint tool to actually annotate the image, and I have some paint tools in here. So you can then color in a little dot and try and connect the two dots using the maze search algorithm. And that maze search algorithm which I have is the Martelli algorithm. Let's see if I can do this. Contour, bug walk, list polys, print polys, single edge. I think it's under heuristics. And it's called process user points. I should give you the lecture on that, because that's a good one. So, once again, the way you run the program, and you can see I've got a whole, package here called Martelli, which does the A-star search through the image domain. But you guys won't want to use that because it's kind of fancy. But if you want to run the program, it's ip.main, and that'll give you the main link into the image processing program about which the book is written. And there's one other image processing program that might be of interest to you. It's j2d.gui.main. In theory, that should work. Work, darn it! Oh, yes, thank you. That was slow. Let's see if we can open up an image. Now you can see there's a shortcut here, Control-O. It's got a much more refined interface. This is a much more modern program. And I think I can get that same space shuttle in there. But here's a good picture. And this is using the multiple desktop interface so that you've got multiple windows contained in a single window. And the median cut algorithm, and we'll discuss some of this later in the course, shows us how we can reduce the total number of colors in a picture. And that color quantization is a part of digitization, right? Because quantization and digitization are, well, quantization is a part of digitization. So this re-quantizes the image. Right? So when I say 2, 4, what that means is I've reduced the total number of levels, of grayscale levels, to only 4 grayscale levels. That's a 2-bit image, right? And here's the image after it's been histogram equalized. And we'll talk a little bit about that through the course too. It's called homogeneous point processing. And I've got a whole little lecture on homogeneous point processing. And if you're in the reading for the book, you're getting out to chapter 4, the homogeneous point processing chapter. Anybody got that far in the reading? No. So maybe it's a good time for me to talk a little bit about what homogeneous point processing is. Homogeneous, what's that mean? The same. Everything's treated the same. They have homogenized milk. Right? What does that mean? It's all mixed up, right? Because normally milk separates and the fat floats to the top. So when you homogenize the milk, what you're doing is you're mixing it up so that the fat globules are evenly distributed throughout the milk. Homogeneous point processing means every point is treated the same as every other point. So with homogeneous point processing, what you're doing is local pixel image processing. So you do something to the pixel, like negate the pixel, then you go to the next pixel, and it doesn't matter how the prior pixel looks, you negate that pixel. So if you turned every pixel red, that's homogeneous point processing. If you turned every pixel inverted, that's homogeneous point processing. Homogeneous point processing is the simplest, fastest, most low-level kind of image processing you can do. No pixel that you encounter is related in any way to any other pixel that you encounter. And so, in some sense, it should be, I think, the first kind of image processing we teach. Now comes this basic software engineering question: how do you structure an image processing program? This is a big question. I've thought a lot about this question. I do not think there is any one correct answer to this question, but I have arrived at a solution. Component software development means being able to have interchangeable parts with your software. The inability to reuse software is a consistent indictment of the entire software engineering community. People write software and then they throw it away. And they rewrite the software, and then they throw it away. And they rewrite the software, and then they throw it away. What a waste! How come nobody can reuse anybody else's software? Why? What's the problem?
Poorly written.
It's poorly written. All right. So now I work really hard and I write this really great software, and now I have to throw it away and start again. Why?
You make a modular design.
A modular design. I don't have... See, what was the thing? What was the secret? The big deal with the Industrial Revolution. Why did we have? What was the difference? I know there was a revolution. I heard about it. I don't think people got real bloody with it. But the Industrial Revolution happened. Something changed. What happened? What was different? Machines? Well, people had machines before the Industrial Revolution, right? The wheel is a machine. The lever's a machine. People are machines. A machine is anything that can transform energy from one form to another. People eat stuff and they make heat. They're machines. Fire is a machine. Converts chemical energy into heat and light. Yes?
Was it the steam engine that started it all?
Steam engines. Ah, very interesting. Steam engines. No, that's a good question. I mean, what about water power? They had water power before steam engines. So what changed? What was the difference? Yes, sir. Interchangeable parts. Key. That's key. With interchangeable parts, Eli Whitney was able to take several rifles apart in front of the Congress and then reassemble them and everybody was astounded. And he promised he could deliver these things, and he essentially made a fortune for himself by making weapons for the Civil War. Interchangeable parts. So it was a big deal. What happened was people in the Springfield Armory were able to outsource the construction of hundreds of thousands of Springfield rifles, and they used the Connecticut River as a means of transportation. Connecticut is an Indian word, which means the long river. Housatonic is an Indian word, which means over the mountain. So the Connecticut Housatonic, which comes out of the Berkshires, is a long river that comes in over the mountain. It goes right past my house, as a matter of fact. So as it happens, that main mode of transportation was the river, and all through the Connecticut Valley, people were able to manufacture weapons and ship them up to the Springfield Armory for final assembly. So trigger assemblies, barrels, stocks, all these things could be made in separate places because of interchangeable parts. But what's wrong with software engineering? How come we don't have interchangeable parts? Well, that's what Java beans are for. That's what component software development is for. It's interchangeable parts that was thematic for the Industrial Revolution, but which the software engineering community seems to have completely lost out on. So what did I do to make the interchangeable parts happen? I decided there would be a single image processing operator. And I would call that image processing operator an image processor interface. And the image processor interface is as simple as I could make it, but no simpler. Right? And here it is. The image processor interface lies at the heart of the image processing framework that I've developed. And the basic goal is that you would input an image, do some processing, and then return the image. And I call that the basic fundamental image processing operator. And so all I need to do is find a way to implement the image processor interface. How hard could that be? And the answer is it could take infinite time, because the number of operators that you can do to an image is not limited. Right? There's an unbound. There's no limit to the number of operators you can apply on an image. Moreover, there's no limit to the complexity of the implementation for the process method. Right? And then if you say, well, geez, what is the impact of the image processor interface's design? Let's look at the usages. And I see not too many. Did I do that wrong? You should be able to look at the implementations. Find usages. Maybe it should be this one. Find implementation, find usages. There we go. So that was fast. But it says there's 119 usages of the process interface. So there's 119 operators that essentially implement the image processor interface. And you can see them pretty easily. There's thresholds, there's homogeneous point processors, there's a bunch of filters, there's something that Gino wrote for doing diffraction range finding. We got video processing. We got it all over the place. Image warping and 119 unclassified usages, edge detectors, color quantizations, animations. It's all over the place. Tons and tons of image processing. So what would be involved in changing this interface? I'd lose my hair, even more than I have already. Right? I'd be pulling my hair out because there's a lot of weight involved in implementing an operator using process, and if you change this and made it so that everybody had to implement one more method, or I changed the argument to the given method, that would be a big deal. Right? That would mean a lot of software development. So everything centers around the business logic behind implementing the image processor interface. And that gives me a nice sort of framework, basic garbage in, garbage out processor. image processor interface. And so when you look at j2d.gui.main, you're looking at the main graphic user interface for the controller of all of the operators in the that implemented the image processor interface. So you could say, well, what happens if I want to change something like the graphic user interface? Do I have to rewrite all the operators? And the answer is no. Now I can reuse my code. And with code reuse, that means I can change my graphic user interface in a big way. And there's a j2d.main in here. And now I have a completely different graphic user interface with the same exact operators. If I click on the doggy, right, totally different interface. I want to go and look at the edge detector. I think I can do this, right? Let's change sigma. Let's try this. Template panel. There's the doggy. It's not looking nice. There it is. Now it's continuously updating on the screen. Right? Sort of. Here's the Sobel panel. I wonder if that'll work. Like continuously. There we go. Going to do a comparison. Here's different Sobel operators. I think that's a yeah, I can rework the display here. So it's kind of an interesting idea, right? You no longer have to worry about rewriting your code. If you have a decent interface that you've implemented, you've basically engaged in polymorphism. Here's the fisheye panel. Let's see if that works. Oh yeah, it works. Kind of log transform continuous update, and yeah. Now that there we go. Lots of operators. That was the polar transform I had before. And here's a Chrome filter. I wonder if I need to hit continuous update on this one. Yes. And so now you can see it's kind of looking a little bumpy and chromy. Is that a word, chromy? Very chromy. Let's see if I can do this edge detector again. I'll try the threshold. Yep, there's the threshold. Now we'll do the Sobel. And that worked, actually. Let's try the Laplacian of Gaussian in here. Now that's not doing anything, but I think there might be a checkbox that I forgot. Maybe not. Some of these don't do what I expected. Oh, that one's working. That's the Laplacian of Gaussian. Oh, it works nice and fast, actually. So, from an image processing point of view, it's not too bad to try and implement the image processor interface. And in fact, everybody can implement their own operators, and we can plug these results directly into the framework for the program. And because there's multiple frameworks, it impacts the program in multiple places. So that's kind of an interesting idea. That means individuals, right? So at first I thought, okay, what we really need is a mechanism for code reuse. But wait a minute. We also have now a separation of concerns. That means everybody can implement the image processor interface and work independently of everyone else, and yet still be on the same team and make a contribution to the same program, and that everybody's results can plug in. So now what we have is essentially like the interchangeable parts, where you can outsource to everybody on the team so that they program to the specification, and then your results can be plugged straight into the framework, and we can all enjoy those results. What a compelling argument for using a standardized interface. Such a simple interface, yet such a profound impact over the life of the image processing program, if you see what I mean. I don't think it's overstating it by saying if you start this wrong, you're going to have to live with it for a long time. Let's see if we got for some reason I had thought there might be some image processing filters left over from students, but I don't see them in here. Oh yeah, here they are. The final was done by the series of students that actually retain their name next to the operators that they implemented. So here are a series of operators that were implemented by students, and they all just plug into the application. So that's pretty cool, right? And I can take all of these menu items and I can turn them into a single panel of buttons. And then you can go through and you can open up an image and apply the buttons one at a time. Let's see if that's true. Take a nice big image. I'm going to try Claire. Oh, that's a terrible image. I'm having so much trouble. Oh, Control O. That's what I should be doing. Control O. Ah, that's much better. Oh, you know what? If I go to color images that are not just GIFs, I can get some larger images, I think. Let's try this one called Girl. Open. Yeah, there we go. That's a little dark, isn't it? Filter flare. Now that's a complicated looking interface. I don't think I want that. Gamma filter. Continuous update. Gamma filter. There we go. Now I can brighten the image. Okay. Close and close. There, that's much better. Hey, nice practical image processing application there. Let's try something different. Adaptive threshold processor. That sounds like fun. And we'll do a continuous update. And now here's a threshold. This must be thresholding on hue, I'm thinking. Oh no, that's height. Wow. Thresholding in a direction. Here's thresholding in another direction. Ooh, that's bad. And I'll hit OK. And close. Some of these filters do things I'm not entirely sure about. This one, continuous update pinch filter. I gotta make this a little bigger. It's kind of awkward because I have a low resolution set for the display here. Continuous and radius. There we go. Right? They're real interesting kinds of filters there. Amount of pinch. You can pinch right into her face. Ooh, that's what happens when you get that aggressive plastic surgery. There's that angle in here. And then a little edge action. See if that does anything. I'm not sure what that did. Transform space, set rectangle. Now I should be able to go through here and set the rectangle area over the transform. And now if I do the radius, maybe that'll change things. Yeah, it makes it a little larger. Cool, right? Slick. Image processing. So you can do all kinds of interesting effects. No shortage in terms of numbers of effects. Here's feedback. Feedback. Continuous update. And now what we'll do is change the zoom. There we go. Feedback. Ooh. And then we'll do a little rotation in there. And then increase the number of iterations so it goes out to infinity. And then I think we can put something in the overlay plane here. So now you've got what is this? Translucence. And I'm not sure that did anything, but that's pretty cool. I like those effects. Those are fun. Now, if you want to do it upright, you feed video in it in real time, and you do this as a video process. And you can do that with Java Media Framework and an arbitrary USB camera, including the one that's built in to this laptop once you have Java Media Framework set up. So that's kind of cool. So there's a little demo. This stuff that I've been doing in here, that's not homogeneous point processing. Right? Homogeneous point processing is a little bit simpler than this. So what I'd like you to do is I'd like you to read Chapter 4. Read about the histogram equalization. Let's see if I can do a quick histogram equalization and show you the effect. For the image called girl, histogram equalization is actually a good thing to be doing. This is called the uniform non-adaptive histogram equalization, and it is the example of the homogeneous point processing in Chapter 4. And you can see right away the impact it has on the image. It allows you to maximize the dynamic range available to you in the image. It makes the colors as bright as they can be without distortion, and it makes the darks as dark as they can be without distortion. And that, in effect, brightened up the image so that for this projection it becomes a lot more viewable. And we'll discuss that a little bit more in our next class. And that's about all we have time for today. You guys have a homework assignment. You have a reading assignment. Everybody have a book? Yes? No? I have books in the office if you need it. And have a good evening. Stay warm. And drive safe. Thank you.